Hello and welcome to episode 3 in the series Particle Physics 101. And today I'm going to be talking about Heisenberg's Uncertainty Principle. Let's get started. Heisenberg's Uncertainty Principle is a principle in quantum mechanics that dictates the amount of information we can know about a particle. Now that may seem a little absurd as to how can there be any quantifiable amount of information that we can know about anything? Just keep measuring it and you get more precise values. However, in quantum mechanics, it's not exactly how it works. Because as I have mentioned before, the rules of quantum mechanics differ from the rules of classical mechanics. So what really is Heisenberg's uncertainty principle? So what Heisenberg's uncertainty principle states is that we cannot, and when I say cannot, I don't mean we don't have sophisticated instruments, I mean it's mathematically and experimentally impossible to determine a particle's position and momentum, as long as they're on the same axis, at the same time. Now this concept is incredibly important in quantum mechanics, since, as I have mentioned, it dictates the rules and laws of nature. So how would we write what I just told you mathematically? So this is how we would write it. Delta x, I'm going to talk about the left side of the inequality in just a moment, times delta p must be greater or equal to h bar over 2, where h bar is known as the reduced Planck's constant, and that equals the Planck's constant divided by 2 pi. Now I have spoken about the Planck's constant in my previous video, which covers wave-particle duality, which I definitely recommend you check out because it's an incredibly important concept to understand Heisenberg's uncertainty principle. Right up there. So let's talk about the left side of this inequality. Delta x. What really is delta x? Now typically we've learned that delta represents change, but in this scenario, delta represents the uncertainty, or for those statistics lovers out there, standard deviation. So I'm going to be talking about the concept of uncertainty in just a few moments. So the delta x, once again, the uncertainty in the position of a particle, multiplied by delta p, the uncertainty in the particle's momentum, must be greater or equal to some constant. Now all this really means is the more certain we are about a particle's position, the more uncertain we are about its momentum. Now, certainty and uncertainty are two very important concepts in quantum mechanics, because in quantum mechanics, most of the time, you're never 100% sure about anything. There's always some uncertainty value with every single property of any particle. To help explain uncertainty, I've conducted a small experiment which I have then recorded, the single slit experiment. This experiment can also be explained via classical mechanics and diffraction. However, we are going to be viewing it via the quantum mechanical approach. One thing to mention, I haven't really used the most sophisticated apparatus in the world because I could only do with what I had, so I do hope you understand whatever you can from the video. But first, let's just talk a little bit about the experiment. This right here, you can say, is the apparatus setup. This is a single slit over here, hence the name single slit experiment. And this right over there is a screen. This is a point light source, which I have used as a green laser. So what you're supposed to do is simply put the laser on, and what you will see is quite obvious. There will be a light right over there, a point source. However, one thing to view right now, and as I have mentioned in my previous video, light is also a wave, or behaves as a wave, and therefore will also have wave-like properties. So if we were to draw this same experiment instead of as a straight line particle as a wave, let's try and do that. So this right over there you can think of is the intensity of the light wave, where this represents the most intense, and this over here, the corners, represents the least intense. Now one thing you can see is that after passing the slit, only this much of the light wave will actually successfully travel. And therefore, we can make quite a large statement over here. This distance can be called delta x, or the uncertainty in the particle's position. And that is because, once again, as I have mentioned, the particle behaves as a wave, and therefore it can exist anywhere on this wave, and therefore there is an uncertainty in the particle's position, because it can be all the way here, more intensive over here, or all the way down there. So let's actually conduct the experiment. So in the experiment, what we must do is get the slit to be narrower. So we start decreasing this delta x, and we get it smaller and smaller. So what you would conceptually and logically think is that, well, why would anything change? Because the light wave is simply going to travel straight and hit the point. So let's see what actually happens. So this right here is simply a point, as you can see, traveling straight through the slit. And as we get the slit smaller and smaller, we can see something really weird. As you just saw, that was quite weird. The light actually started to grow instead of shrink, which is extremely counterintuitive. So let's actually draw out what happened. So we are going to be assuming that this is the narrow slit. I know it really doesn't look narrow at all, but just for visual purposes, let's take it as it is. So what we saw over there was definitely really weird. Now, as I have mentioned, this is not the most sophisticated apparatus in the world, but I really do hope you could understand a little bit from it. One other thing that we didn't really see is the light is also supposed to be illuminated on the other side. Once again, because of my lack of equipment, I couldn't really produce the wave required, but theoretically, I could show you what should have happened. So this is typically what should have happened. The light wave should have been very concentrated over there, which we saw, I'm pointing to right now, and then concentrated over here as well. Unfortunately, once again, because of the apparatus, this part didn't really appear, but that's all right, as long as we understand the basic gist. So once again, the light wave, most intensive, would be there. But once again, if we remember, this distance is the uncertainty in its position, because, as we remember, light acts as a wave. So how does that really happen? Why is the light spreading instead of getting smaller and smaller? And this is where we finally refer to Heisenberg's uncertainty principle. As we get this delta x, or the uncertainty in the position, smaller and smaller, basically, as we get the slit smaller, we are raising the uncertainty in its momentum. Because as we can see, the smaller the uncertainty in the position, the larger the uncertainty in the momentum, because they are inversely proportional to one another. And therefore, instead of the momentum vector being straight, we get that right over there. And this will now be acting as our momentum. And this is going to be acting as our uncertainty in our momentum. So now let's try and actually derive a certain expression for this scenario so that we can kind of get close to Heisenberg's uncertainty principle. Now, one thing to note, the math required to actually prove and derive Heisenberg's uncertainty principle is more advanced than what I have already covered. So we're not going to be doing anything too advanced, but just sticking to the simple analytical geometry. Now, because there is uncertainty in the momentum, we can say, let's say this point over here also travels there. And let me call this angle theta. So what can we do with this? The first thing I want to do is drop a perpendicular line to this over here. Therefore, this is going to act as a triangle. So let's take this triangle and make it a little bit bigger. So what we have here is that this is a right angle, and via some simple geometry we can get that this angle is also theta. Now this side over here represents delta x over 2, because as you can see we are taking half of this distance. So then what's this distance over here? How do we even find that out? Well, the first thing we must see is what is the image on the screen. As you can see, this part over here is a destructive interference, which basically means when this wave and this wave cancel each other out. So when will that happen? Two waves will destructively interfere when they are out of phase. So what does that really mean? That means one wave has to be like that, and the other one has to be exactly opposite, like that. So when we put them together or superimpose them, a flat line will be produced, and they will destructively interfere. And that's essentially what we're trying to say. So when is this true? When will this wave destruct with this wave? Or what does this distance have to be such that they can cancel each other out? Well, if we see the distance between both of these crests, we can say that this distance is half a wavelength. So we can finally label this side of the triangle and say that this has to be lambda over 2. So we can say that sine theta equals opposite over hypotenuse, and therefore lambda over 2 divided the uncertainty in the position divided by 2. So we can simplify this to get sine theta equals lambda over uncertainty in position. And finally, we can make an expression for the wavelength, where the wavelength equals the uncertainty in the position multiplied by sine theta. So now let's try and make an expression for our momentum. Now, taking this point as the point of reference, we can also say that this line can represent the momentum of the light wave. So finally, we can say that sine theta equals opposite, which is the uncertainty in the momentum, divided by the hypotenuse, which is the momentum, since this is a right angle triangle. Therefore, the uncertainty in the momentum equals the momentum multiplied by sine of theta. We're almost there. We're very close. So I just erased it so that we can have a little clearer view of what I'm trying to prove here. What can we say now? One other thing we know from Louis de Broglie is that the wavelength equals Planck's constant divided by momentum. This I have already proved in the last video. So what do we know about the wavelength? We know wavelength equals this right over there. So we can say that h over p equals uncertainty in the x times sine of theta. Finally, we can get Planck's constant equals the uncertainty in the x multiplied by p sine theta. We know that p sine theta is the uncertainty in the p, and we can finally get that the uncertainty in the x multiplied by the uncertainty in the p. Now, I don't want to say exactly equals because we have made a few assumptions in this proof. So I'm going to say roughly equals Planck's constant. And this is an easier way of deriving Heisenberg's uncertainty principle. Now, the reason they're not exactly equal is because in the proof I have taken a few assumptions that are mathematically generally not taken. And since we are not doing any rigorous mathematical proof, but just showing you the general idea, I'm not going to get too deep into that. So this, ladies and gentlemen, is Heisenberg's uncertainty principle. I really do hope that you enjoyed that video, and hopefully the experiment that I conducted helped you a little bit into understanding Heisenberg's uncertainty principle. Until next time, stay sharp.